So it's searching and querying knowledge graphs with Solr and SIREn. And a little simple reference architecture for doing this. Let me give you a little bit of our background, where we come from, and how we actually got to Solr, because we weren't starting from that. So our goal, we started in 2007. We were building, it was a research project. I used to be a senior research fellow. I raised considerable funding for an idea which was making a search engine which was dedicated to this very fascinating world, web of data, semantic web. So in other words, we kind of ignored the text. We went around the web. We kind of ignored the text. There's a lot of search engines that would do text. And we were interested in annotations. Nowadays, you find it everywhere. It's called schema.org. It became very popular. Google actually, said it's a good idea, and the other fellows. But that's now. But a few years ago, 2006 and 2007, it was pretty new. There was some annotations around there. Microformats was a big thing, and others. And that's what we were focusing on. So we got to the point of getting 700 million documents, right? And out of these 700 million documents, we were extracting triples. So subject, predicate, object, all connected, making a graph. Our graph had about 30 billion edges, and it was, it was a big thing. It was a considerable time ago. We had a good cluster. It was about 50 machines. We were using Hadoop, HBase, and all that to process, et cetera, et cetera. But we wanted very fast search. Now, there are still today, and in fact, we're using them, triple stores. Triple stores are graph databases where you can pump all this, and you can make nice queries, et cetera. However, that's really not something where you can go like in production speed. It's really not something where you can throw it 100 queries per second. They're meant for complex query, but not for very fast, slightly simpler queries. And that was where we had this idea. Renaud Delbru was joining then, was starting his PhD, and said, look, why don't we try to use Solr? I say, well, Solr is for text. That's for text. No, we can do more. And that's how SIREn came to be. SIREn stands for Semantic Information Retrieval Engine, as a plugin on top of basically Lucene, /Solr, and now Elasticsearch as well, where it's very, very efficient to encode structured data, like trees, into the index. Right, so that's where we came from. We had analytics. That's the content of bbc.co.uk. It would analyze and ultimately give you a very fast search that was also containing structure. Right, so what we're going to be showing today, what is a knowledge graph? Goals and ways to approach searching a knowledge graph. Then a very simple, I'd say, reference architecture. And then demo, I don't know if we get the demo, and then some conclusions. Right, so what is a knowledge graph? You might have heard from Google a lot. I mean, if you just Google up knowledge graph, you'll find a nice page. It explains you. It is about connecting all the knowledge together. You can think that, Leonardo has been painting La Gioconda, which is at Louvre, which is in France, et cetera, et cetera. You get the idea. Now, as a knowledge representation people, coming from the entity relationship world, well, what you can think is like a huge database. It's a relational database because all these things have relations, right? It's just with a humongous schema with possibly, tens of thousands of tables. And then where the columns, you got basically add them freely because today you might learn something new that doesn't fit into anything. And in a knowledge graph philosophy, you want to be able to add it because even if you don't use it today, you might use it tomorrow. So you want to have the tools to be so flexible. And these are knowledge graph tools, right? Facebook, Yahoo, and all the other fellows, kind of buying into this concept. And so what is an enterprise knowledge graph? We think it's the next big thing in enterprise because it's not going to replace definitely, your production-grade databases, your oracles and whatnot, but it's a very useful tool to have to explore new ideas, and especially for knowledge-intensive enterprises. I mean, this was a very large customers dealing with publications in the bioscience world. They had a lot of publications. You want to extract a lot of fact, do mining, whatnot, put it into a graph. Then you have your domain ontology, possibly even million of terms. You want to do some enrichment, enhancement, and then there is so much data available out there freely in the bioscience sector. You want to be able to integrate, leverage it, ultimately get even your customer to put their data in your knowledge graph and be able to deliver very smart new applications of all sorts of things, very customized, very specific things exactly for your doctor, exactly for your patient, combining all together, right? So Freebase is a knowledge graph. It's a very well-known example from Google. It was a company, it was acquired by Google, and it becomes kind of like the core of Google Knowledge Graph. And we have a Freebase distribution. I mean, we know the people very well, the Google guys. We have a nice Google developer video you can watch. And we have a distribution. It's completely free. You can go on SyndicateTech, which is kind of our second name. SyndicateTech is more the knowledge graph side, and SIREn solution is more the Solr. side. And you can go there, you can download it, and you can spin it up very easily on Amazon or on Google Cloud. And you have your own freebase. You have your own huge colored graph, and you can go ahead and queries. And it comes instrumented with a few tools that make it easier to understand, because like I told you, the schema is super complex. This is one of the tools we provide in the distribution. It's a data type explorer. You can type in some, and you can see how richly, incredibly nested the types get to be, and how entities have so many types at the same time, and what's more popular, what's less popular. At the same time, you can write this complicated Sparkle. Sparkle is a query language for graphs that we use, but you're also assisted. So we're using MapReduce, we calculate analytics, and we make it easier for you to make queries. Now, I won't get into too many details. A little bit of, this is just a very subset of the relational data. So you have films, for example, connected to directors, obviously, to ratings or whatnot. But sometimes it's even more complicated. For example, you could say, well, there is an actor in a movie. Well, not really. In a movie, there is a performance. And the performance is by an actor of a character. So it becomes kind of complicated. And so this is a schema level, and it's already, it's like a 0.1%. But if you go on instance level, it's even more daunting. I mean, this is like infinitely simplified. It's Forrest Gump. And you can see the Forrest Gump is connected to another node, which is the performance, which is then connected to another node, which per se doesn't have any label, right? But you have to go, once again, one hop away before you find the string Forrest and Gump. So 1, 2, 3 hops away in the graph. And how do you think these graphs are managed by graph databases? They're basically joins. They're a bunch of joins. They're huge tables, subject, predicate, object, or with some provenance maybe. But so it's one of these. It's like you're merging on Forrest Gump alone. You're probably merging something like well over 2,000 to 3,000 records in the triple table before you can have something which represents in a very meaningful way Forrest Gump. So what do we mean searching a knowledge graph, right? Well, sure, I mean, short. So, well, you want to search something like Forrest Gump, you want to say Forrest, the film, you want to put the names of the actor, and you still want to find the movie because, they're far away in the graph, but you still want that node that represent them. And, or you want to do semi-structured search, which is really cool, something similar to a database. Well, give me a movie where the actor is English and the character is American, and it contains house somewhere in the text. So something in the middle between a database, you want to be able to sort, rank, have facets, and cost effectively, production speed, hundreds of queries per second, possibly. So nothing to do with graph databases. So challenges are many, but I think at this point, I'll pass it to Renaud.
So what are the challenges in searching the knowledge graphs here? So as we can see, the knowledge graphs have quite a complicated schema and usually quite large. And you have also arbitrary entity relation, so that doesn't follow usually the schema, like in a database. And also, another side problem, small problem, but it can be have some consequences is you have usually lots of multi-valued, textual multi-valued attribute, and if not properly handled, you will end up with a false positive result in your search. And also, we want to search relational data. So we want to search entity based on information from the entity related to it. So for example, we want to search a film based on the certain attribute of the actor or the character of this movie. At the moment, what are the current solutions that we have to search a knowledge graph? So here I will just go quickly over a summary of the different approaches that we can use here. So the first typical approach is just using a plain Solr, so you flatten the data, one document per entity, and you will flatten the relationship, for example, the name of the actor or the nationality of the actor into a single feed attached to the film. So this is relatively easy to implement. The problem is that you lose completely the relationship and the structure of the data, and this also increases the amount of false positive results you will add. And also, since you don't keep the structure, then you have less chance to make advanced ranking. So you can only use primitive ranking. So to overcome this kind of problem, there was this relational and nested data-aware approach where that you can divide it into two sets, query time joined and index time joined, each one with a pro and cons. And each one, for example, query time joined is good if you have lots of updates, because you can update quickly an entity without having to do too much work. On the other side, you have to perform join at query time, and therefore, your response time will be low. And on the second solution is index time join, so you will materialize everything at index time, all the joint. The problem is that, yeah, in terms of updates, if you have an update, it's likely that you will have to reindex many documents. So there is a trade-off here to analyze and to apply here. And at the moment here in this reference architecture we will show you, we just focus on plain index time joint. And later, yeah, we will plan to start integrated query time join and to be able to use this trade-off into the application. So query time join, so how it works, yeah, you have one flat document per entity. So for example, yeah, you have one entity for a film, for each performance, for each actor, and then at query time, yeah, you perform the join to compute the relation between the entity. The advantage, yeah, is either to index, either to update. The problem is that, yeah, if you look at this knowledge graph schema, you will quickly end up with a huge amount of join to perform. And if you want reasonable response time, you will have to load loads of data in memory, so you will have high memory requirement. Yeah. Block joint, which is a feature implemented in Lucidworks and Solr, is also using, yeah, one flat document per entity, but it will index, it will compute at index time, yeah, all the relation and the join. Yeah. How it will do that is that it will put in the same block, document block, all the entities that are related to each other. So for example, here we will have the entity film, and we will put in the same block all the performance and actor entity related to it. So this works well for small and well-defined schema usually. The problem is with block joint, you have usually some upfront effort required to design the system, and if not properly done, yeah, you can end up also, yeah, with a false positive result. Yeah. And also, yeah, the main problem is the increase of memory usage. Yeah. So you can see that for each nested entity or each related entity, we'll have to create a new document. And therefore, yeah, it will artificially increase the number of documents in your index. Yeah. And given that you artificially increase the number of documents, then the memory usage increase. And for example, if you start to want to use facets, then you end up with lots of trouble. So we develop SIREn, which in a sense is very similar to block joint, but on lower level is quite different. So it's similar in the way that it is an index time join, index time model approach here. So it is implemented as a Lucidworks, Solr, and Elasticsearch plugin, and you can see it as a plugin to index arbitrary JSON documents. It supports, yeah, nested object, nested array, data type, proper support of multi-valued textual attribute to avoid false positive. It's completely schema agnostic, so you can just push arbitrary JSON. It will take care of indexing it for you, and you can query it right away. Yeah. And the advantage of SIREn versus block joint is that, yeah, you can handle more large nested model, but also you have a much better memory usage. Why? So look at the right, there is a document. So in fact, yeah, it will not create one document per nested entity, but it will create one document for the full tree structure, JSON tree structure. So you have a film with multiple performance, and each performance has multiple actors, and what it will do is that it will annotate each entity with a specific ID. And the particularity of this ID is that it encodes the relationship between all the entities, the ancestor-descendant relationship. And if you can just have to match, so for example, the film with 1 and the actor with 1.1.2, match and see if there is no overlap, and to detect if it's an ancestor-descendant relationship. So I will not describe more in detail this, how SIREn works. You can, if you're interested, watch the talk of last year of Lucidworks Revolution. There is a full talk on this year. So to come back to the reference architecture, so why we develop this reference architecture? The problem is that to index the knowledge graph, there was no generic solution. So usually, yeah, you had always ad hoc solution, and with custom code specific for a specific type of graph or an end user app. And we would say custom code, say, yeah, costly to maintain, limited extensibility, etc. So what we did is that, yeah, we tried to abstract all these steps and create a reference architecture to reduce custom code by using generic standardized tool. And also, you know, the reference architecture, one requirement was to quickly adapt to change in the data schema. Yeah. So for example, if you have new schema, if your data schema change, or if you have new data requirement in your search, you should have the least modification to do as a code or in the pipeline to support this. Yeah. Giovanni, you want to?
Yeah, so very quickly, the reference architecture is you have a free, like a knowledge graph, can be as large as you want. In this case, it's, was it 2.7 billion triples or something? So it's quite a big one. And so, well, what you would do is you would generate the basic entities. You know, basic entities, it could be just simply subject, predicate, object. They're not very sophisticated. It's just one hop away. And those are very simple to generate. You could not even need Hadoop if you want. And those kind of like a baseline search because they contain labels, it contain descriptions, so it will give you something decent. But at the same time, yes, we're using a graph store because they're pretty handy. I mean, they can't be very fast like real-time search, but definitely for building an index, that's going to be helping us. So we load it there, and we have a set of templates, which we will discuss. And with the templates, use, for example, the Sparkle language in order to compose a much simplified, but still structured document. So still nested tree, which then goes indexed in Solr with SIREn on top. And that gives you a pretty good search. I mean, you can search those things. You can search things based on properties of attributes. You can do semi-structured queries because you still. So it's like for certain entities which you care more about, you have templates and you can make your search better. For the other, which is just baseline, you just have a baseline search. That's the good thing about this is that you can allow your customer to, you know, tweak certain templates so it becomes the search becomes smarter where they need to. Okay.
No. So let's look at the pipeline of this reference architecture. Yeah, I will describe the main steps. So the basic idea is that we use the RDF stack for all the pipeline. So RDF is a generic and standardized way to represent graph data. We are using also Sparkle for the extraction and mapping phase of the graph, and JSON-LD to export this smaller graph into JSON tree structure. Yeah. And you will tell me, why using RDF? Yeah, we can use, there is a lot of different graph tool available. The thing is that here we are using RDF because, it's standardized, it's supported by major GraphDB, and it means that, we are not tied to specific backend system, and it's quite useful. For example, if you switch from one customer to another, if you have different GraphDB backend, you don't have to rewrite the full pipeline to adapt to the system. Yeah, this is the stuff. So the first step is extraction and mapping. Usually is where the major effort is involved. The first step is to extract a graph subset of interest from the huge knowledge graph, and then to map it to a simplified schema. Why map it to a simplified schema? Because graph schema usually are much more verbose and complex for flexibility reason. And for your end user app, usually you just need a more simplified schema. And this also will simplify the search and query at the end of the pipeline. And for this, so we use Sparkle, which is, you can see it as a SQL for RDF graph database, and the construct operators that I will explain next, which allow, compared to SQL, the select of SQL, allow to build graph as output instead of table. Yeah. So it works as extraction and mapping. So it's a similar approach to data import handler for Solr, where it's working in two steps. First, you have a query to retrieve all the identifier of the entity, and then you have a second query to extract the graph and map it to a simplified graph. So I will show you quickly how it works. So here, the where clause is where the extraction occurs, and the construct clause is where the mapping occurs. So if you look at the graph example here on your left, the first statement will extract the label, the title of the movie, and map it to a title attribute in the final graph. Yeah. Then we have this second statement that will extract all the actor node 2 hop away and map it and attach it directly to the root of the film entity. And then the last statement that will extract the attribute and attach it to the movie. So here is just a simple example, but to show you quickly how you can quickly extract and map it complex graph. And so this is also the main place where you will have to write custom code. So in the other part of the pipeline, it's practically automatic and dynamically done. Yeah. So after we have now a set of subgraph, a graph that represents each entity, and we want to transform it into JSON in order to index it into SIREn. Yeah. So we use JSON-LD and a technique called framing that force a specific tree layout to the graph. Yeah. And from the graph on your left, you will generate the JSON document on your right. Yeah. So from this point, we have lots of JSON documents for each entity, and the next step is to load it into Solr and SREn. SREn, by default, you can push it and index. The problem is that at the moment, we don't support, for example, store field or faceting, etc. And for this, you need to use native Solr field if you want to support this feature. So we created a update handler that in fact mimics the Elasticsearch API that will take a JSON, indexing the full JSON into a SIREn field, but flatten also the JSON into a set of Solr field that can be stored, used for facet and so on. And the schema is updated automatically using the managed schema of Solr. So this here reduces the design effort. So yeah, you can push arbitrary JSON and you don't have to work on your schema. And also, yeah, for example, if your Sparkle query change, you change the pattern, you want to add new attribute to a certain entity, it will dynamically update and dynamically take the change. So here, I just quickly give you an overview of the update handler. So here, yeah, you configure it. You can configure it based on path-based mapping. So it tells you, okay, for this actor.nationality path, just use the field type string for indexing. Then you can have type-based, so all the values of type string will use the field type text. And here is just the mapping for the SIREn field and the default mapping. Yeah. So given this, now you can just push. This is a request to the update handler of SIREn. You can push directly a full JSON document, and it will take care of indexing it for you. And then you can start querying it. So here you have a query, a node query, which is a specific operator of SIREn, but you can see also that you can use the facet field actor nationality that has been automatically extracted by the update handler. So normally we have the demo, but I'm not sure
I don't think,
this is working.
no, the interface is still locked.
Yeah.
We had loaded 60 million entities plus all the advanced trees into an index, but that computer is
So Giovanni.
yeah, sure. So apologies, we don't get to show, but also the time wasn't very much. So, well, you can imagine that you could do those queries that we were telling you before. So both unstructured kind of high quality, meaning that you're looking for terms which are far away, and structured, so really like query-like databases, plus the facettings and everything else. Now, how do you update, right? Because this is a fully materialized approach. You might say, oh my God. Well, first of all, I mean, a lot of time with MapReduce and whatever, the whole thing will rebuild maybe in a few hours. So if it's okay for you to change every day, you can just rebuild it. But then you can actually do much better. But for example, SIREn, one of the characteristics of SIREn is that it allows you to match a node, even if it's inside a tree at any level, arbitrary, and you don't have to specify where it is. It's like, look, tell me which documents contain a certain sub-documents, no matter where it is, and SIREn will tell you. So what happens is, let's assume that there is one new entity. You can ask SIREn with a query, and it will tell you, well, it's also there, meaning that you also have to reindex the other documents. So for updates, which are a small percentage of your full thing, you simply ask SIREn which entities to rebuild, and you can then reuse, for example, assuming that you keep your Sparkle endpoints, and also reindex the other entity in which the first entity was materialized in order to provide this advanced search. So that's pretty simple. Yeah, so I'll be wrapping up, and say, well, knowledge graph doesn't immediately match your typical search problem because usually you have documents, and here you have these very tiny little things, very highly connected, so you have to go around and pick them up and put them into a document, right? So you have to go and traverse the graph a lot. So you need an efficient strategy, and a strategy which, if you want to have high quality and be able to do semi-structured, has to be able to do joins, in a sense. There are very efficient way to do query time joins, index time joins. Query time joins are also coming with other architectures. So what we've shown you is a very simple architecture that uses Sparkle, which is very handy to do this. Sparkle would give you a new RDF graph, a much simpler one, and then from that RDF graph you want to get to JSON. You use JSON-LD for doing that. And once you have JSON-LD, version 1.4 of SIREn, which is out basically since 3 days available, you just pump your JSON directly into Solr, and it does the schema and does everything for you. And by the way, it's extraordinarily efficient. I mean, you should look at the white paper. When you have very complex JSON, it becomes immensely more efficient than the alternatives, which is block join. So yeah, so still there is customization to do. It's not like because you want to craft these templates in order to have the better searches, but it's better than not having anything. So for more information, you can look at SIREn solution, where you can download the plugins. It's all free and open source. And if you want to get the free-based distribution and just launch your own knowledge graph in the clouds, just go syndictech.com/freebase. That's all for me. Thanks.